Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to our pre-lab lecture. This is going to be our last experiment. Please check your grade book, make sure that everything has been accounted for. Email me if there is any discrepancy. That's one announcement I would like to make before I proceed with the pre-lab lecture on electrochemistry, in particular, using the Nernst equation to calculate the cell potential at non-standard state. But first, let's just look at some of the definition, review some of the concepts, some of the key terms you have learned, or some of the terms you learned before we go through the data sheet and how to proceed with the calculation. So the title today is on electrochemistry, the Nernst equation. I'll explain later on or show you what is equation and where it is used. But first, what is electrochemistry? Electrochemistry is a branch of physical chemistry that concern with relationship between electrical potential and identifiable chemical change. The chemical change you will see in this experiment is redox, the type of reaction, identifiable reaction which will take place. So why is electrochemistry so relevant to our day-to-day life? It has application in fuel cells, sensors, supercapacitors, battery testing, and so many other applications which I don't want to dive into. Let's go back to the basic of the type of reaction which you should know. All right, the type of reaction. All right, we call redox reaction. Redox reaction. This is a type of reaction transfer of electron or electrons. All right, a reaction in which there is chemical or there is transfer of electrons from one species to the other species. We call it redox or reduction. We call it reduction. Oxidation reaction. In other words, redox reaction is an abbreviation for reduction. Oxidation reaction. There are two types of reaction taking place, which is oxidation reaction. Oxidation reaction is a reaction where there is loss of electron. Think of loss of electrons. There is loss of electron. We say oxidation has taken place. And then there is what? Reduction reaction. Reduction reaction. This is gain of what? Gain of electrons. Gain of electrons. If you want to learn this, there's a oil rig or oil rig for mnemonic committing to your memory. Oil for oxidation is loss of electron. And then Rich is reduction is here is low gain of electron, gain of electrons, yeah, gain of electrons. And remember, electrons are negatively charged. A species which gain a neutral species, if it gains an electron or gain electrons, they become negatively charged. If a neutral atom loses an electron or more than one electron, they become positive or cation. That's one thing you need to understand as far as the two types of reaction is relevant to our experiment today. Now, uh, this type of reaction, they do take place at the same time. There is no way an electron is just lost into nowhere. One species is losing an electron to the other species. We can split this type of reaction into what we call half reactions. Okay, let's say half reaction. You read in the background in the lab manual, there are reaction where one reaction and then there is reduction, half reaction. We can split the two reaction into what we call half reaction. Let's see if a species, for example, loses an electron, such as zinc, going to zinc equals positive 2. This means 2 electrons have been lost by zinc to become ion. Here, 2 electrons, making this oxidation reaction. And then, if let's say we draw a parallel between these two, see U positive aqueous gaining 2 electrons, U solid. Here reduction reaction. How will I know that reduction has taken place, or this is reduction, this is oxidation? Is by keeping track of oxidation numbers, which is the overall charge. If you look at this, is 0 going to +2. So oxidation can be also identified by increase in oxidation number. This is an oxidation because of what? There is increase in oxidation. This is +2 increase here. You see +2 going from 0 to +2. But decrease, if you look at from +2 to 0, this is +2, there is decrease in oxidation number. I hope you recall what is oxidation number. Oxidation number. Now, reduction, all right, reduction can also be identified by keeping track of oxidation number, and anytime you see decrease in oxidation number inner spaces, and then you know that there's a reduction. So that's how you can use to identify reduction, oxidation, reaction, oxidation, reduction, reaction. Now, we can write a net balance equation. This is what you'll be using in the lab when zinc, which is solid, react with, or this is a galvanic cell, which we'll see, plus aqueous going to zinc 2 positive plus Cu solid. We consider this as product reagents. We have here reagents, and of course, here products. Reagents and product, just the way we have we use the or we read the chemical equation. We have the reagents on the reactant side, or on the left side of the reaction are products on the right side of the reaction arrow. This is a representation of voltaic cell, which you will see later on. So if I look at this or identify here, this going to here, there is a loss oxidation reaction. How do I know there is loss of what? Loss of electrons, loss of electrons from an oxidation state of 0 to positive 2, oxidation reaction. And then this is going to from positive 2 to 0. So gain of 2 electrons. So this is reduction. There are terms which you need also to commit to your memory in terms of what? Reducing agent. This is reducing agent. The one adding or donating electron is referred to as reducing agent. The one making the other species to lose is called oxidizing agent. It's quite confusing. Nationally, students do have a challenge in divining these about 6 terms associated with redox reaction. What is being reduced is an oxidizing agent. An oxidizing agent is reduced. Reducing agent is oxidized. So these are the terms you need to learn as far as the redox is concerned. Now let's look at the reduction reaction and look at how electricity in electrochemical reaction, how electricity is generated. We have 2 types of cells: voltaic cell and so sometimes this is called galvanic cell. And then this one, electrochemical cell, which we are not going to look at. Voltaic cell uses spontaneous chemical reaction to generate electricity. All right. When a chemical reaction spontaneously takes place, electrons are transferred. In the process, electricity is generated. Whereas electrochemical cell, it needs external source of energy to drive the electron to move from, point A to point B, or from cathode to from anode to cathode, which we will see momentarily. All right. Now, in voltaic cell, we can split it into two. You should be able to draw the voltaic cell or galvanic cell. Consists of two half cells, what we call, these are the two half cells. I'm constructing a voltaic cell with what we call the soul bridge. And here is the anode, and here is the cathode. We have here electrode, we call here, this is electrode. This is an electrode. It's just a piece of metal. You'll see that in the lab. We call this electrode, and there is a wire. You're gonna use a voltmeter here to read some force. And then going to another electrode. And in your case, you'd be using copper. You'll be using zinc. And here is zinc sulfate solution. Here you have copper sulfate solution. I have drawn an galvanic cell or voltaic cell with the two half cell. We call this a half cell, and this is a half cell. What takes place in anode? Okay, at anode, oxidation take place at anode. Okay, loss of electron. Here there is loss of electrons. So that what we have is zinc going to zinc 2 plus. And remember to write the physical state solid aqueous plus 2 electrons. The electrons will be transferred in this direction, electrons from anode to cathode, from anode to cathode to electrons, or just electrons, let's say electrons, from anode to cathode. And then here there is reduction reaction. This is the Cu 2 positive aqueous plus 2 electrons going to copper 2. It's just copper solid. That's copper solid. So at the cathode, reduction this is where reduction takes place. In terms of copper 2 ions reduce to copper, reduced to copper at the anode or at the cathode. In this case, note that electrons are pushed to cathode. The electrons are pushed to cathode from here. You see the electrons on this direction so that it reduces the ion. I don't want to go in details into what happened here in terms of how the ions and how the metal is stripped and how the copper is electroplated on copper electrode. Now the soul bridge here, you're gonna have KNO3 or KCl used in the lab just to provide the flow of ions so that the cell is complete. Now, how do you know? The question is, how do you know that this is the anode, this is the cathode? Why not the other way around? Should we memorize and just say this is the only galvanic or voltaic cell we have to be worried about? Suppose we have other elements other than zinc and copper. Or in the data sheet, not data sheet, but in the lab manual, I'll show you how to identify the anode and the cathode, especially when you are just given an equation similar to this, that how do I know this is cathode, this is anode, how do I know that zinc is losing electron and copper is gaining electrons. Suppose even it is like just molecular equation, how will you know which one is the reducing agent, which one is the oxidizing agent? I'm going to show you in a moment, but first, please learn how to, not for the lab, but if you're taking the course right now, please learn how to reproduce or draw the diagram of voltaic cell. Now we can calculate the voltage right here at standard state, right? At standard state, STP, we talk about the standard cell potential, which is E. You see this E, so it stands for standard cell potential. Is given by E cathode minus E anode. Anode. The equation you see here from, let me show you from the calculation. But from the procedure, standard cell potential. This is how you use this equation for the cell potential. E superscript node cell stand for cell potential, which is given by E anode minus E cathode minus E anode. There's a list or the literature standard reduction potential for different elements as the ease at which they are reduced. And I want you to look at the standard reduction potential involves is negative. Let me even blow this up. It is negative. If you look at it is negative, more negative, it is positive. So what is happening here is the electrons, remember we are talking about the electrons. Electrons flow from high to low potential. In other words, if you think about what happened in your cell phone before you run out of the juice, there is high potential, and then it will reach a point where the anode and the cathode, there is no flow of electrons. So electrons flow from a more negative. More negative is always the anode in the cell potential. The one with the more negative standard reduction potential is what you will do. You will assign as the anode. The less negative, even though you may have both of them negative, the less negative will be the anode, not necessarily to be positive. For example, here, negative 2.375 and negative 1.706. This will be my anode, that's more negative, right? And then cathode will be negative 1.706. So you use these standards reduction potential to identify which one is the cathode, which one is the anode, in order to calculate the standard cell potential. And I will explain why we say standard cell potential. Now, one more before we move on. If both of them have cell are positive, if you look at this, this is more positive compared to positive 0.15. This is positive 1.49. In this case, this will be my anode, even though it's positive, my anode, because it's more, not more positive, but less positive. This is more positive. This will be the cathode. This will be the anode. So that's how you identify the anode and the cathode. If you are not given, or if you don't know any, or if you're given any other elements other than what we have in the worked example in the lab manual, as far as this equation in the quiz, there will be, you will calculate the standard cell potential for anode. And by the way, I forget to put a superscript there, which is coming from this table. You'll be given this table if need be, or you will be given the information to the effect of standard potential, so like in here. So now, when we say at standard potential, remember the concentration at standard condition. We are talking about 25 degrees Celsius and 1 molar. We use the superscript. All right. E node, standard reduction. Reduction means we are adding electrons. We are reducing all the elements here. Adding electrons, standard reduction potential. This superscript E node is because of at standard state, that means it got to be 298. All right. Changing to Kelvin, 298, 25 plus 273. And 1 molar, that's the concentration of all these species. We talk about the standard state. So that's all what I wanted to tell you as far as calculating the A standard cell potential. It is the cathode minus the anode. This should be anode. Let's make sure you can write anode. Let me say anode. That's how you use this equation for standard cell potential. You'll be using this equation. Now, as far as the data sheet is concerned, all right, I'm going to show you how the equation, the Nernst equation at, all right, non-standard state. That means if at non-standard state, right here, we talk about E cell, there is not a subscript or superscript, sorry. You know, it's not, you don't see that. There is nothing here. Equals E, which you are going to use the previous equation from here to calculate E, minus, all right, 0.05916 volts over N, and then log of on that side, log of here, concentration of the product over concentration of the reagents, concentration of the product over concentration of the reagent, where, all right, where N equals to number of electrons transfer, number of electrons transfer, N stand for number. How do you know that, you know, how many electrons are transferred? By the overall positive charge, you can tell that XYZ electron, if it is positive 2, then it's going to be 2 electron loss. And for your information, there will be 2 electrons being transferred in this experiment. What you will do, we call this now the Nernst equation. We call this Nernst equation, which you will use in the experiment to collect the data. You will be working at non-standard state. What do I mean by that? The molarity will not be 1 molar. Therefore, it's a non-standard state. The temperature will be something else other than 25 degrees. It could be 26. It could be 27. It could be 28. It could be 22. But it's non-standard state. So we use Nernst equation to calculate the cell potential at non-standard state, which we plug in this, we call the Nernst equation, which we'll use that. So now let's see how you will complete the data. Just like in the last or one of the experiment we looked before, I numbered the boxes in the data sheet. This way it will help you in, you know, if you get stuck, you want to email me, I will be able to identify which line number. I'm going to use line numbers based on my numbers here, that line number 1, line number 6, line number 7, line number 15, 16, and so forth. So when you email me, just refer to the line. You have to reconcile this data sheet with the procedure. I don't want to have, or rather maybe I can, let me see, I think I can have a parallel between the procedure. Okay, that's calculation. Yeah, right here, the procedure. You need to read the procedure here, understand, recall some of the skills you learned previously we have been using, because some of them you'll have just to recall and use it in calculation. So let's see item number one. Please read the instruction. Using graduated cylinder, you'll measure, the reagent from the fume hood. If I look at here, concentration of ions in the experimental cells, once you construct that, how do you calculate the concentration? For number one here, all right, for number one or line one, molarity is given by number of moles of volume in liters, concentration. But you're not gonna be calculating, it's already given, given from the instruction, molarity of, all right, when you construct, this is 0.0. Three significant figures. I meant to show you this. This is the molarity. For line one, you have that. Because of what? Right here. The first thing you need to do is solution, get 50 ml. Oh, this is how you just have to identify. This is 0.025 molar copper 2 ion. For cell number one, you will be performing, all right, here, you will be performing 4 experiments. This is cell number one, cell number two, cell number three, cell number four. So for cell number one, the concentration of Cu, this is concentration of Cu, Cu2 ion is already given. Now, for cell number, for zinc will always be constant. You're not going to change that. For cell number 2, this is where you need to pay attention on how to calculate the concentration of all right, concentration of the copper 2 ions. You need to increase, if you read here, okay, you need to increase the concentration by 0.25, concentration by 0.25 right here. Once you have the voltage determined for cell number one, solution, carefully weigh out enough anhydrous copper 2 sulfate with a molar mass of 159.62 to increase the molarity by 0.25. So cell number 2 here, you need to see how it's increasing. The molarity is increasing from the molarity is increasing from 0.25 here. No, molarity increases from 0.25 to 0.50, all right, 0 molar, 0.050 molar. So that is the concentration. If you look at the number of moles for cell number one, number of moles, then I have number of moles is given by what? 0.012 5 moles. For cell number 2, all right, number of moles equals to 0.025 500 moles. That means if you increase the concentration from 0.25 molar to 0.500 molar, the increase in number of moles from increase in what? Increase in number of moles 0.0500 minus 0.1 no 0.125. This is cell moles. Here is what moles. This is moles of Cu. This is Cu for cell 2, and this is for cell 1, increase in number of moles. So this is number of moles increase. So the number of moles which increases from point. So we have to increase in order to get this. Let's see. In order to get the molarity increase from 0.25 to 0.500 molar based on right here, to increase from 0.25 to 0.50, this is the number of moles we need to increase. Therefore, mass of CO4 needed to increase, all right, needed to increase the concentration of from this is from what this is from 0.5 increase from 0.25 to 0.500 is 0.1 2 at 0.0125 from here, moles times molar mass, which is 159.62 grams per mole. And by the way, here, so that we reconcile the grams, this is grams of copper 2 sulfate. So mole and mole will go away, and turns out to be 1.99 or 988 grams of CS04. This is how much you will mass out in order to increase the molarity. So remember, to increase the concentration from 0.25 to 0.5 here, you need to mass out 1.99. From 0.50 molar to 0.75 molar, you'll have to mass out 1.99. Remember, you don't change the solution. All you have to do is keep on adding to increase the molarity. So mass out, if I were you, I will mass out what? 1, 2, 3. I'll mass out 1.99 3 times. Once I'm done with cell number 2, I add 1.99 to make cell 3. Then I add 1.99 to make cell 4 and so forth. Each time you need to increase the concentration of copper 2 ion, And then you will measure the cell potential. This is from the experiment. What you read, you will read that what is the measured cell at non-standard state. So this is from the experiment. But here, you need to use the Nernst equation right here. I'm gonna use the Nernst equation, which I gave you here. The Nernst equation, I think it's given in the procedure. Let's see how Nernst equation will work. This right here, or if I come here, the Nernst equation, this is just for the cell. I'm gonna use that to find standard cell. But here, if I want to find this on the data sheet here, all right, this data sheet, you have to use the cell right here, okay? For 5, 6, all right? For 5, 6, 7, and 8, this is the equation you will use. And now you may ask, what is a concentration? And remember here, N equals to 2, all right? Maybe I should have here the numbering from here. For 5, line 5, all right, line 5, 6, 7, 8. All right, so it's lines 5, 6, 7, and 8 there. Use Nernst equation. This is what I'm writing. No, you are wondering. Use Nernst equation, which is E cell is given by E cell node, which is the standard cell potential, minus 0.05916 V, all right, over 2. 2 electrons will be transferred. This is false, by the way. Log of from this equation, this is the equation we are going to use right here. It's the same one we have right here, okay? This is the equation, log of the concentration of, all right, concentration of product, which is the zinc, over concentration of copper. So for each cell, all right, for each cell, you need to look at the concentration of copper, concentration of zinc ion concentration. And I think it is going to be one constant. You don't change, or you will not change the concentration of copper throughout. What will change is the concentration of copper from cell to cell, from cell to cell. If you look at the charge, +2 means we are losing 2 electrons. So for 5, 6, 7, and 8, use Nernst equation. You need to find the concentration from each cell. And then here, for percent error. Percent error, it's under calculation. It's under calculation. Let me see, where is my calculation? Let me just minimize this right here. All right, if I minimize this, okay, yeah, right here, calculation. Whichever, look at percent error here, whichever is, all right, negative or positive, theoretical, measured is what you measure right here, and then calculate it right here. Theoretical, maybe you can just hear theoretical, This is from what? Nernst equation. And then, of course, measured is the experimental. Measured experimental what? Experimental value. Experimental value. You know, this means absolute. You just have to change or make it what? Make it positive. This means absolute. You will change it to positive, whichever is small, whichever is small. And by the way, here, this is what you need for the last column in the data sheet. So we are done with table 1, how to complete item 1 through 8, measured, use Nernst equation, use the equation given here to find the percent error. Remember that is absolute. Let's move on to part P. Part P is determination of the formation constant. All right, maybe even I should label this as here. Let me explore this part P. Part P here is simply experimental determination, all right, determination of formation constant of copper NH3 4 and 2 positive. Let me make sure that we get it right. Make sure we get right the formation constant for this complex. Yes, this complex right here, copper 2. All right. Copper 2 complex with ammonia, the formation constant for that. And we will use the Nernst equation. Once you have the cell complete, take note of what you will measure: 20 ml of what? 15 molar ammonia. And be careful with this, it stink a little bit. We always recommend that you add in the fume hood to avoid, ammonia fumes in the lab. Please add the 20 ml in the fume hood and make sure you stir it for quite some time. All right. So at this point, you have 20 ml of ammonia and 50 ml of 1 molar copper 2 ions. So 50 plus 20 is 70 ml, 70 ml of solution. It's important to know the volume, 70 ml. Now, this is a limiting reagent problem too. Remember how you determine the limiting reactant using the stoichiometry. Remember the equation. We're gonna come back to that. This equation. This equation right here. This is the stoichiometry for 1 mole of copper 2 ion, 4 moles of ammonia react to form 1 mole of the complex. So 1 mole of copper 2 ions produce 1 mole of. And if you look at this, the formation constant, which is Kf, let me just show you. Kf is given by concentration of the product. All right, concentration of the products over concentration of the reactants, which is given by concentration of the copper 2 complex with ammonia, 4 with the 2 positive, over concentration of copper 2 times concentration of NH3. And remember, this is at equilibrium. This is at equilibrium. This is at equilibrium constant, okay? You look at this equilibrium expression, these are equilibrium concentration. Therefore, we will calculate the concentration of copper 2 ion at equilibrium, ammonia at equilibrium, and the complex at equilibrium by completing the table 2 or the table on part P. Just like in table 1, I will use my whiteboard to show you how you will complete each item. For number 10, right? For line 10, number of moles is given by volume in liters times molarity. How will I know that? How will I do that? You have the volume here and you have the molarity. To get the number of moles, remember M1, I don't even know what M1 V1 is. It's just number of moles times the volume, which I do have it here. It's not M1 V1. Don't use the dilution law. So for line 10, figure out what's the number of, what's the molarity is given, the volume in liters. You should be able to change that, give you number of moles. Likewise, for 11, number of moles, this number of moles of NH3, all right, is given by volume in liters times molarity of NH3, which is here. You got to change that to volume in liters. And then this is the molarity for line 11, okay? That's what we need to use in this, in line 11, molarity. All right, let's see this. Maybe I can even, I should have just minimized this. I can move it here and then split my screen so that we have that. Yeah. So line 11, this is the equation, number of moles of ammonia is volume times molarity. Initially, before you mix the two reagents, okay, we don't have the complex. It's the number of moles of complex, therefore 0. Now for line 12, all right, for line 12, all right, for line 12, how are you going to find that? For line 12, use the stoichiometry. Stoichiometry. From the balanced equation, we know copper 2 plus 4 Na3 in dynamic equilibrium with the copper, the complex of copper with what? Ammonia. This is 4:2 plus. Mole ratio here is 1, or rather it is 1 to 4 to 1. 1 to 4 to 1. So we need to know how many number of moles of Na3 consumed, since Cu2 positive is the limiting reactant. How do I know it is limiting reactant? If you look at these black bolded plugged parts on part P, it means nothing is left over. All right. In quotes, we assume that everything has been consumed. Number of moles of copper is consumed. Nothing is, it's the limiting reagent. So we need to determine how many moles of ammonia from the total from line 12, or no, from line 11, so that we know how many it's left of. So it's going to be line 10 times 4 moles of NH3 over 3, no, 1 mole. This is 1 mole, not 3, 4. 1 mole of 1 mole of 1 mole of 1 mole of copper 2 plus, and this will give us let's say x moles of Na3 consumed. Therefore, 12 is given by line 11, what we started with, minus xxx consumed, or rather consumed, which is moles of Na3 consumed. That's how you find line 12. Please go back here, how to find based on the mole ratio. I use this to find the number of moles consumed, which is line 10. It's gonna give you the number of moles you plug in there. So you have that. Line 12. This is line 12. Now, for line 13 is equals to line what? Line 10. Why am I saying that? From the mole ratio, look at the mole ratio. For every 1 mole of copper consumed, 1 mole of the complex is produced, so that if we look at this, if I know line 10, what I started for copper, I should know the number of moles of line 13 here. So line 13 equals to line 10. Whatever the number of moles you have will be the number of moles of at equilibrium. If you look at the last column here, all right, last column, we need to find, leave alone 16 first. Let's look at 14 and 15. For 14, line 14, it is the molarity equation. This is equilibrium concentration, and for molarity. So molarity of what? Ammonia, Na3. It is concentration of Na3 at equilibrium is given by what? Is given by line 12 over 0.075, no, 0, not 5 liters. Where am I getting this from? 50 ml plus 20 ml. You see that? We are adding 20 ml and 50 ml combined volume of 70, change that to liters. So the concentration of ammonia at equilibrium is given by line 12, which you should have, divided by the total volume. That will give you equilibrium concentration of ammonia. 15, this is the equilibrium concentration of the complex Na3 4 to positive, and it's going to be equilibrium. It's given by line 13, all right? This is line 13 over 0.075. 0.070. Again, right here is 50 plus 20 ml. Yeah, this is where the 70 ml. Now for 16, yeah, for 16, use Nernst equation. Use Nernst equation. You remember, I didn't mention anything from line 9. This is just what you will measure. Where 9 or line 9 is measured E cell, not standard, but the cell potential. This is cell potential at non-standard state. What you measured in the lab. I'm gonna use this in order to do what? To use the Nernst equations. And following what? Or yeah, let's say follow the worked example in the lab manual. I will show you how this worked example was used, which means the equation here is E what? E cell, this is line 9, is given by E cell. Calculate this. You need to calculate this. You can calculate this because we are using zinc and copper. It's the same cell we used before. This cell, I don't know if we have it. No, we don't have it right here, but I think it's given in the procedure. It's given in the procedure. So you need to calculate the E cell minus 0.05916. This is falls over 2. This is over 2, not 3, over 2 electron. This is going to be 2 electron transfer, that is false, over log of concentration of zinc is 1.00 molar. This one is concentration for zinc, right here. Concentration for zinc over concentration of copper. This is what we are looking for. So here, this equation, you should calculate this. This is from line 9 to electrons, 1 molar concentration of zinc, but we are looking for this. I want you, when I sort of follow worked example in the manual, see manual, yeah, right here, I think somewhere down the line here, that using the Nernst equation to electron transfer, the worked example is right here. All right. The worked example is right here using this equation. All right, using this equation. So E cell, this is what you will use as a line 9. You have to calculate, don't use this value. You have to calculate for zinc and copper, standard cell potential for zinc copper to determine the is cell. 2 electrons. Instead of lead in this worked example, you'll replace with copper. Instead of lead 2 ion in this worked example, remember you're gonna get this from your experiment. It's just gonna be the same thing as you see here. Dividing it 2 is gonna be the same thing. So you should have a setup similar to this. Some number here from the experiment. This is the standard cell potential minus whatever you have it here, log of this. So instead of lead, you're gonna have copper. And then follow all the way until you have the concentration of copper. You have the concentration of copper. This is a Charles Marx, which I don't want to get into details into the logs. Remember, lead, concentration of lead will just be the same as concentration of copper. So that you now have what all the information you need to calculate the formation constant. You need to calculate the formation constant. This is what I wanted to say, that the formation constant for experiment is the concentration of, all right? This is from the Nernst equation right here. All right, from Nernst equation, from the Nernst equation. And once you have that, this will be experimental. You will determine, let's see what is we have on the data sheet, the formation constant. You calculate the percent error. You see this, compare your value with the literature. This is the literature, 1.2 times 10 raised to positive 13 in order to complete the data sheet. I think the data sheet is right here. This is calculated formation constant from this equation. And percent error, right? You know percent error, absolute value. I think we have in calculation percent error. You're gonna have percent error. Excuse me, there's a train going through, so please do that, and then you'll have the percent error. Submit the data sheet at your earliest convenient time. Please do submit the data sheet at your earliest convenient time. Other than that, have a nice day. I will end the lecture right now. Please email me if you have any question. Refer to the numbers if need be, so that it's going to be easier for me to get back with you. Other than that, thank you.